到这样这种到3分，今天小心点，对，不要说。
哎，Seng还没回来，风不进去啊？啊？直接，哎，哦天，宿醉啊，宿醉。大学生的生活多姿多彩啊！等考完试再写。Okay, let's recall the definition we introduced yesterday. Hopefully, today we will introduce the definition of topological space. Okay. So, well, let's recall. Let X be a metric space. Okay, and then we look at some certain subset of X metric space. So, what is the interior point of A? Okay, let's say interior point X of A. What is the definition of an interior point? 啊，哎，你下来，什么 open ball? If X in there, continue. There's this R greater than 0 such that X is in A. Okay, so actually you just require there exists an open ball. Okay, that center at X containing in A. Okay, don't even need to require X is in A, but the consequence of this definition is X has to be in A because I require the ball to be in A. Okay, so it's a consequence. No need to specify explicitly. Okay. Second, if exterior point if there exists also an open ball similarly center and X, but it is in A, C. So if I want to draw A, maybe first case A is like this, and then A may be outside for the second case. Okay. So these definitions are very pictorial. You can draw it out. Okay. Third, exterior point is a point, boundary point. Okay. Boundary point. How about boundary point here? If the quantifier change, right? For boundary, you need to check for all open ball. Okay. All the open ball around X. All the open ball around X. Will intersect A and intersect AC non-trivially. Okay. Okay. What's the point we introduce again? Limit point. Okay, how about limit point here? What do you need to check? What do you check? Huh? About every or there exists. Start with every or there exists. Every, huh? Every open ball around X uh-huh, must contain an element in A that's not equal to X. So how do I write this? Maybe I take this ball, intercept at A, okay? It's equal to S and something else. Okay? X and something else, not just X. Okay, such that this Y cannot be equal to X. Okay. Last one. Okay, last one. What's the last one? What's the one more point we introduce? Limit point. Isolated point. Okay, isolated point. Let's isolated point here, very special now. This isolated point must pick from A. Okay, outside one 跟 A 没有什么关系，没有什么好讨论。Okay, when we want to talk about isolated point of A, we need to talk about the point in A. If there exists an open ball around X such that when you intersect A, it is just X. Okay. So all these balls have a positive radius. Okay. So to be precise, the existence and universal quantifier here all referring to this R. Okay? All referring to the R. Okay. So then we will define the closure. Okay, the closure A bar of A equals to be A bar equals to A union the limit point of. Okay. So yesterday we mentioned that this limit point could also be inside of A or outside of A. Boundary point also have this property. Could be inside A or outside A. Okay. So there seems to be some relation between these two types of points. Okay. So we will prove a bunch of propositions to let you see how they are related. So let's bring this page up. Copy. Yes. Okay. So yesterday we stopped at this proposition here. Let's go through them one by one. Okay, let's go through the first one. A limit point of A need not be a member of A. So need not be means what? Could be or could not be. Okay. So give some examples that both cases could happen. Any example you can give? Is X any A you can pick such that its limit point could be outside or inside. Question. So what's your A? What's your X? What's your X? What's your A you can consider here? Huh? What's the space you want to consider here? Huh? Q? And then A then? You want to change? Then to change the example. How if you take X as Q, how do you take A as R? So you want to change example. Huh? Change example. You want to continue? What's your A? X is R, A is Q, then then every point in A is a limit point of A. Any limit point of rational number is not a member, is not a rational or not. Yeah, what's that? What's that? Hmm. Huh? You have to continue first. What? I think this example works. Right. So you simply take a irrational number, right? There's a sequence of rational that converge, right? Okay, so if you draw out this picture here, you got an R, right? And then you got all the rationals. Let's use this line as your rational. And then if you pick some irrational here, okay, then limit point, what do you need to do? For every or there exists? For every open ball, right? So if you look at every open interval around X, it should contain some rational number from A. Okay, why? Because rational number is dense in real number. Okay, so let me write down. So consider X to be irrational number. Any ball around X. So actually, you know how this ball looks like, right? This is just an open interval. And based on the matrix we had on real number will contain a and rational number since rational number is dense in okay. Dense in R means for every two real number, you will find a rational number. So in particular, for this two real number here, okay, you will find a rational sign. Okay. Any other limit point or not? Any other limit point? Rationals are all the limit points of this set also. Okay, so if you consider again, let's say y in the rational number, again, you take any ball around y, okay, x minus x plus it will also contain an rational in the set in A that is not equals to that's not equals to y. Okay. Again, since Q is dense. Okay, let me ask you a more technical problem here. Just now I just tell you between two real numbers, I can find an irrational. But now I tell you can find another one. You know what's the problem here? Who knows the segment tells you between these two, I find y for you. Then you got a trouble here. But because you need For a limit point, you need another point that is not equal to y. Can you use the density property to find another irrational that's not w no? And that's not y, sorry? Can or not? Let you think 1 minute. Sorry? How? How to find this w using the density again? Huh? Yes. So, well, you know that. Yeah, let me go it. Well, you know that y is in between x minus r and x plus r, right? So instead of picking these two real number as your ingredient, you can pick y and y plus r. So using the density will tells you that between these two numbers there's a rational. Okay. And so the between there is strictly between. So you will know that this number is not different from. Okay. Yeah. So you yeah. 帮我写吧，写 x 对哦 thank you 啊。So here should be y. Okay. So you need to make a clever choice here. Yeah, make a clever choice. Okay. Right. How about the second statement here? Okay, how about the second statement here? If x is a limit point of A, then every open ball center at x contains an infinite number of points from here. Okay, so from the definition, right, it just tells you that there's contain one member other than x. Okay, but here says that there's infinitely many. So how do you cook up so many points? Okay, from just one point then. Okay, how do you cook it up? Yeah. What? Contradict? No need. You can just keep creating. Should I just draw it for you? Don't write the word. Huh? Let's draw this for you. So let's say this is a point, a limit point of A. So let's draw our A out. Okay, let's draw our A out. By the way, I have a writing inside the notes. If you want, you can read it later. So it means what? If you take any ball, okay, any open ball. Okay, I'm being lazy. This is open, not closed. If it's open here, or maybe I use the other one to open. If I have an open ball here, it means what? It will contains one more point. Okay, one more point that is in A, but not equals to x. Okay, maybe somewhere here. Okay. Right. And then the claim is, if this is true, this ball should have infinitely number of points from A also. How to find the infinitely? Using the statement, you know that for every ball must contain other member than x. Huh? Did you see some distance between here? X and Y. What can you do is you pick a smaller ball. Still a ball around X. Limit point tells you what? There will be other member inside here other than X. Read Y1. Again, you play the same game. Pick a smaller ball again. Okay, and then you can find Y2 here. And then go on. So actually the infinite number here, where can you see? You see the distance reducing, right? So it's like how many number in between is in between the interval, right? Remember? But we prove that an interval is like infinite many. I mean, actually as big as C. Okay, so you can keep repeating this process. Okay, now 0.1, 0.01, 0.0001, 0.0001. Okay, so you can enumerate it. Okay. Okay, makes sense, huh? Okay. So I didn't write down the word, but you can read it. Um, so as what I say, 3 is very trivial because we already defined A bar to be A union the limit point. But the problem here is why the other inclusion doesn't work. Do you have examples or not? And why the other inclusion doesn't always work? Do you have example? So you need to, I think we gave an example, right, just now. Just now we just gave an example, right? Huh? We gave an example, right? Okay. Q is a strictly subset of R. Okay, actually R is a closure of Q. Okay, if you take all the limit points together. Correct or not? How you define R? Limit point of Cauchy sequence of rational numbers. That's how you fill out your fill out your rational number. Okay, all the gaps between rational numbers are the irrationals. Okay, so before finding irrationals, actually your numbers is like much discrete. Okay, after you fill in the irrational, only you can draw this line out. Otherwise, it's still discrete. If no rational number, irrational number, you still live in discrete math. Okay. Fourth one. Every point in A bar is either a limit point or an isolated point of A. So how to prove this kind of statement? Or you need to show for all, right? So just pick a point from A bar. Okay. Then two possibilities, right? X is either in A or X is a limit point of A. If it is a limit point of A, then you are done. Okay, because it's a limit point. If, uh, if the later case happen, then we are done. Okay, suppose now it is not a limit point. Haha. If it is not a limit point, what do you do? What's a negation of a limit point definition? For all become there exists a ball such that there's no other member of A inside there. So meaning what? B R X intercept A is the singleton X containing X. So which means X is a isolated point of A. So from here, what did you see here? So actually, when we define limit point and isolated point, they are actually negation of each other. Can you see the symmetry here? Okay, you must see the symmetry here. For example, interior point and exterior point. Okay, what's the symmetry? Okay, one is inside A, one is outside A. And then what is the symmetry between interior point, exterior point, and boundary? Okay. And one is boundary, you need to intercept both set to be non-empty. Okay. And then you check for both. Okay, so pretty straightforward. Okay, last one. X is in A bar if and only if every ball, okay, greater than 0, contain a point of A. Okay, let's start this. What's the significance of this? What's the significance of this? If you are either a point A, the ball around this point obviously contains a point of A because you already pick point of A. Okay. But let's say you pick the point from the limit point of A. Just now we said that this limit point are not necessarily live inside A, could live outside A. But this theorem tells you that even if you live outside A, you make the ball around any ball around this point, you can find a member of A. Although you are not inside A, OK， 你没有住在他家，但是他的家人一直在你附近，是吧？听起来很像鬼故事。OK, OK, yeah. Okay, so let's try and prove this. Okay, let's do two direction here. So from part, yeah. So if X is in A bar, then from the previous part, we will know that it is either a limit point or a isolated point. Okay, so just now we just prove it. Isolated point. Okay, so well, I mean, if it is a limit point, then we are done actually. Okay, if it's a limit point, then we done. Because limit point give you the point in A for any ball it makes around it. Then we're done. But if it is an isolated point, if it is an isolated point, we also done, right? Because the isolated point has to be in X in A. Okay. So okay, it is also easy if X is isolated point. Oh, okay, meaning one direction is easier. How about the other direction? Okay, let's suppose the other direction. Suppose that for every BRX, okay, it contains a point Y of A. Okay. A becomes small. Here A is big, right? A. Suppose that for every ball around X contains a point Y of A. Now we want to show that X is either inside A or it is a limit point. We have two possibilities. Well, I mean, this points, okay, let's study from this point here. So then it might be the case that Y is not equals to X. Okay, so meaning is other point than X. Okay, it could be not equal to X always, or actually, sometimes it is X. It is X that is inside A. Okay, sometimes it is X inside A. You understand what I say? Yeah, sometimes. Yeah, let me draw it. Let's draw it. So whenever we say ball, point, make sure inside your mind start draw this ball and point in your mind. Okay. So if I have a ball on X here, so it could contain some Y of X. Sometimes it's not equal. Okay, sometimes it could be equal. Okay, sometimes not equal, sometimes equal. Okay, or sometimes equal. Okay. If you can always find Y that is not equal, meaning what? In the former case, X is actually a limit point, limit point definition. Okay, for every ball, you can find some other member. Okay, in the second case, if you only in the second case, what is the definition of that? Let me write it out. Meaning there's some ball around X such that B row X intersect with A is just X. But what's this definition here? This is isolated point. Okay, so you are either a isolated point or a limit point. Okay, so in both cases, by definition, actually X is in A. Okay, I have examples inside the lecture notes, but I don't want to present. I will let you read it itself. Since you can accept this idea here. Any question? Any question before we move to the next part? X, 哪里？ X is a limit point of X. 对，错了。X is a limit point of A. Thank you. Okay. Next. So theorem. If we have a subset of Rn, okay, then what you can observe here, actually we try to collect what we have here. If you take a closure of A, actually it is the complement of exterior of A. Okay. And then second, what is A bar actually? Okay, A bar, so here A bar is A plus limit point. On the other hand, it is just interior plus the boundary of A. Okay, interior of the boundary of A. Number three, A bar is really just A union boundary of A. Okay. So if you take A, close out, take all the limit point, is the same as you take A, put all the boundary back. Okay. Not that here didn't claim that boundary of A must be equal to limit point of A. Okay, there's no claim with that. Because you don't know this union is joined. Yeah. So there's no claim like that. So be careful. Maybe I'll test you. Okay. So let's try and prove them. Let's put out the definition of A bar here. So A bar is equals to A union limit point of A. Okay, so I mean, this proof is set equality, right? So left to right, right to left, okay. But in fact, if you write down the condition, it's always if and only if. Okay, let's try that. Let's prove it in one go. So observe that depends where you want to start. Doesn't matter. So let's start from exterior of A with its complement. So complement of XA. So what does this mean here? By set theory, X is in X, okay, obviously, but X is not in the exterior of A. Okay, so you spell out the definition, no? Okay, not in exterior of A means what? There does not exist a ball around X such that it lives in the complement. Okay, but what does this mean here? There are few cases could happen here. There's no ball around X that could live inside the complement. Few cases could happen. Yeah, few cases could happen. So for every radius ball around X, what happened? It could be all living inside A, so that you don't have any radius of ball can live outside. Or what? Or it could be the case that for every ball you make, the intersection between A and AC is not empty. Okay. But both of these cases suggest what? Either it is a isolated point or either it is a interior point. Or okay, so let me put here. So in the first case here, there are few cases could happen. It could be well, I mean this just implies that X is in A, right? Okay, first case, yeah. And then second case is boundary point. Okay, boundary point. Or is this a limit point? It's also a limit point, right? Point here. Huh? Depends what kind of intersection you have. Yeah. If this intersection has something else, then X itself, that will be a limit point. If it doesn't have X, if it doesn't have any point other than X, but this ball intercept A must be non-empty, meaning what? X itself is in A, otherwise nothing is in A. Correct? Otherwise nothing is in A. Okay. If there's no other point than X is in A, but still non-empty, meaning what? This X itself is in the intersection. Yeah. Okay, so in both cases, so either X is okay. So let me put here if so let me label this as B. This is A. A, I already tell you it is in A, but if B happens, either Y not equals to X is in BRX, or 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 there's no such Y in BRX, which implies that X must be in A. Okay. Okay, so before that, I need to say that this Y have to come from A. 如果你在这个圆圈里面找不到 A 里面的人呢，但是你要 intersect A non-trivially， then 哪一个点需要在 A？X 一定要在 A。Okay. So in any case, this implies that X is in A. Okay, how about second? Second. How to prove the second here? Even you know one already. Yesterday we proved that we can split this Rn, right? This only work with Rn. Let me see. Oh, I set this as Rn only. Okay, let's fix it as Rn. Does it matter or not? Okay, let me check. Does it matter? I think it doesn't matter. We can make it more general. Make it X. Just metric space. Okay, so yesterday we split our metric space using A, right? Into what? Interior of A, union, exterior of A, union, boundary of A. Okay, and then moreover, this union is disjoint. Okay, the pairwise intersection is empty. So you see, A bar is a complement of XA. So what's the complement of XA here? Interior A union boundary A. Okay, done. Okay, from top right. Okay 吧 The complement of exterior A 另外的东西。OK， 你只剩下 interior A 和 boundary。Okay, part 3. Part 3. Part 3, how to show part 3, Okay, part 3 got a very interesting way of writing it. So let me show you. So let's keep the goal here. I want to show that A bar equals to A union boundary. Okay, so what do you know here? We know that in A should be inside A. Okay. And because last time we showed that if you are in A, you are a point in A, X must be in A. Okay. And then A obviously in A bar. Okay. Okay or not? Okay. So let's play a game here. So from previous, so we have proven two segments, right? Must be useful one. Whenever you see in mathematics, we list in order. Usually the previous segment will be useful to prove the next. Right? So that we list them together. Okay, so we need to use the previous part. So by part 2, we know that A bar is equal to in A union boundary A. Okay, by this case here, what can you see? We know that in A is also in A union boundary A. Okay, so we got one direction already. A bar to A union boundary A. Okay, so we need another direction. This A union A bar, sorry, A union boundary A have to be in A bar. Okay, how to go to the other direction? Okay, we can continue. Okay, continue with the assumption we had. So we know that A is also in A bar union boundary A. Okay, we play the same game. A bar we know that is interior A union boundary A union boundary A. But this is just interior of A union boundary A. But this is what? Up to A bar. Okay, we close it. Okay, so this boundary A is like a 零 加上去加上去。You are adding the same thing. Okay? Does it make sense? Yeah. So should I show you picture first? Okay, before I show you picture, let's go to the next one first. Proposition. Let A equals to a ball. Let's look at this open ball. Okay, just open ball. Inside a metric space. Then we can try to ask, what is the interior of this open ball? What's the interior of an open ball? It should be just the open ball itself. Okay, that's why we call it open ball. 里面每一个点都是，我还没 define open it's an interior point. Okay, so later we will define open using this property here. 每个点都是 interior point. And then exterior of A will contain all the points such that dyx is greater than r. Okay. And then how about boundary of your open ball? Okay, your boundary of open ball should be living in the set of dyx equals to Okay, this one is a bit interesting, This one a bit interesting, Why not equal, Why not equal? Why not equal? A bit interesting here. Why not equal here? 如果你想这个圆圈的话，肯定是应该要 equal 的。Something else will happen, it's like just okay. Later I'll show you. Lastly, what is the closure of your ball? Okay, closure of your ball is all the point that is distant less than r. Okay, this one obvious now. All right. I won't prove it to you. You can try yourself, but I want you to see one example, one counter example to the other conclusion that it's not always true. Okay, so for example, let x equals to the set 0, 1. Okay, and then we're going to define this matrix here. So D01 is 1, D00 equals to D11. So you should check that this define a metric. This define a metric. For any 2 point, I tell you what the distance already. And you should check that this satisfies positivity, symmetric, and triangle inequality. So I didn't tell you what is D10, right? So to make it a metric, meaning what? D01 has to be equal to D10. And then you check whether you have triangle inequality. Well, let's look at the ball. Look at this ball here. Ball of radius 1 around 0. What is inside this ball here? Only 0. Contain 1 or not? Why doesn't contain 1? Huh? 1 is on the boundary. Okay. Oh, shouldn't answer like that. You should answer from definition. 1 is a distance with 0, exactly 1. Okay, but ball you need strictly less than 1. Okay, there's only 0. Okay, then what can you see here? Actually, you can check that interior of A is A, exterior of A is 1. But what's the boundary of A? What's the boundary of A? What's the boundary of A? Can 0 be a boundary of A? Can 1 be a boundary of A or not? Why? Huh? Sorry? You should use the ball definition, intersection ball definition. So being boundary of A, what you need to satisfy for all open ball or there exists. For all or there exists. For all, right? For all ball around 0 or 1, it should intersect 0 non-trivially, intersect 1 non-trivially. Can you always do that? No, right? Yeah. Smaller one. Do you need very small one, right? It had a radius one also enough, right? Okay. Once you take a radius 1 ball around 0 and 1, you won't see the other point already. Okay, so if you have a 0 here, 1 here, and then we say that this distance is 1. Okay, and then you make a 1 ball around here, you won't see 1 anymore. But you being a boundary point, you need to intersect your complement non-trivially. But if you make an open ball around 1 with radius 1, you also won't see 0 anymore. Okay. So actually this boundary is empty. And then you can check that A bar is equal to A. Okay. Okay, what time is it? Okay, let me show you another picture, then we can take a break. So I put these picture together that you see. So if you look at this picture, can you recognize which one is a limit point, which one isolated point, which one boundary point? Huh? Which one limit point, which one boundary point, which one isolated point? Huh? No, yes. Why you see the McDonald? I purposely put a McDonald here. Catered for you guys. That's why it's not a limit point. Yeah. Okay, so where are the limit points? Where are the limit points? This one. I purposely draw so many for you. This one is one of the limit point, right? This spiral thing are also limit point. You see, here not limit point. But you can see that if I use this open ball, right, meaning that this point here is not living inside the set. And so the limit point could be outside the set, could be inside the set also. Boundary points, these are the boundary points. Okay, the blue part one are the boundary points. And isolated points, actually all the M here are all the isolated points. Correct. You can draw a small ball around it and avoid all the other points. Yeah. Okay, you see, being a limit point, you should have, if you make a ball around it, you should have point inside A. Or actually it itself is a point of A. If you don't have some other point inside A. Does it make sense? Okay, I try to include all the cases inside this picture. Okay, in case you see some cases not in there, you can inform me, I draw it in. Yeah. Huh? Oh, sorry, oh, yeah, sure. Yeah, fine. Yeah, okay, yeah, that's fine. No, I'm trying to say like what's the condition that limit point, isolated point, and boundary point can get. It's not about open set yet. Yeah. But you could. So I mean you could like those here, the other side. Hey, we haven't defined close and open yet. Why we are talking about close open here? Okay. So there's a Uzumaki there. Uzumaki. Uzumaki. We got star, we got moon, a flower, got fish. Okay. Any more questions? Got question? Sweet. Come on. You just include it. If you want to replicate also can. Just include it. Okay. All right. Let's take a break until 457. That's 407.什么？
你自己看，
反了？反了。
错了。别，这个石头它有一点点容易破，所以你就稍微拿到温柔一点点。
好，错了。
哎，头发，你这边是不是也应该设计subset？
subset 咩？没有等于咩？
为什么是等于？
我看下我有份吧。
你这个都是 partial union 那个了，你不是等于？
对啊，我这边写 last tree 哦，怎么我这边写等于？
对，怎么可能是等于？
啊，我正什么？我在这边有正吗？对哦，怎么我这边写等于？
你这等于了，你这边不是那个
对
axt 也会等于，因为它是
对
两个 complement，
对，可以这样讲。
所以一个是他弄错的。
这个 proof 就是为什么是 all bigger than zero in A，或者是 all R？为什么不能是 some R？
还有可能
some R？
还有其他可能你是说啊？
是
等一下，
some R inside A，some R intersect，两个都是。
你是说一些 R 会 intersect？
就是比如说大一点的 intersect 这两个都当 empty，然后小一点的就 intersect，就是感觉哪里怪怪的。
你觉得这个怪怪
就
？OK，
这个这个好像不是所有的情况。
OK，想想 ，as 一个 R，如果没有一个 R 是全部活在里面的话，就会有，只要有一个是不是就可以了？如果不存在一个 BRX 活在这个里面的话，就是说其实每一个都会 intersect A non-trivially，对不对？我只需要知道这个就好，不是？我只要需要这个就好，就可以了。
就是每个都会 intersect A，对
non-trivially，其实我懂这个就好，其实。
non trivial，为什么是 non trivial？
因为不然的话，它就会整个活在 AC 里面。
不，BRX BX 不在 AC 里面
BRX 不存在一个 BRX 在 AC 里面，就证明每一个 BRX 都要 intersect A not trivially。其实这句话就可以证明我是在 AA8里面，是不是？更简单一点。
它为什么不能是每一个 intersect 它都是 X？就 X 在 A 里面的话，
可以啊，可以 X 在里面，可以 X 在里面。如果 X 不在里面就
我以为 non trivial 的意思不等于 X。
我觉得那个更简单哦，这个更乱一点，那更简单吧？应该它每一个 R 都要 intersect A not trivially，管你怎么 intersect，反正就是这两种。
我还在想，就是这可不可以说，就是你每一个 R 你对于所有 R 大于0，它都 intersect 不 empty，就相当于是你 along all the sequence in R plus。如果你 along all the sequence 的话，
什么？再来一次。
就我感觉就是，如果你是对于所有，就相当于是 R bigger than zero，然后 intersect A 都是 not empty，然后这样的话，你就是 along all the sequence，就是因为 R 大于0就可以列成所有的。就一样，就所有的大于0的。然后 sequence 的话，就是假设其中一个 sequence，然后这个 sequence 就是对所有 sequence 它都 contain。我的意思是，如果是 infinitely intersect A complement 的话，它就是那个它就是 boundary。如果是 only finitely intersect A complement 的话，它就是那个interior of A。
你是想要确认它是什么点吗？
但是我觉得就是，如果需要一番的意思的话，你说 R 大于0，相当于所有 sequence，然后就有点麻烦。那样的话，对于就是 mutually 比较好用。
我觉得我的证明是直接用4就可以了。因为你如果每一个 R 都 intersect A non-trivially 的话，你移的是这个，移的是这个，应该就可以用到这个。
让我走一下，好最近。
可以直接用4。你应该是你想知道它到底是什么情况？
对，就是如果 limit 换成 infinity，如果是 particular 就是 finite 或者没有，就是对，就是这个。
OK， 你的应该是说，如果是 eventually constant 的 sequence，其实它就是 isolated point 来的。但是如果它不是 eventually constant 的 sequence，它就是一个 limit point。
就是你 R bigger than zero，然后你有一个 sequence of boss，就是 BR。然后就是你就是 Rn 是一个 sequence，比如说 one half，
对，
然后这样，对，就是如果是有 infinite number of BR intersect A complement non zero，它就其实就是 limit point。
对，
然后如果是 finite 的话，就是 isolated。对，但是这样的话，如果你没有数列数的话，就很麻烦，就到底怎么说R bigger than zero equivalent to all the sequence， 就感觉就
喂，什么？你要说什么？
因为我们we have 就是 all R bigger than zero， 然后 intersect A complement intersect A non empty。
对。
但是我现在是用 sequence，你怎么能说 sequence 跟 R bigger than zero 是一样的？所有 sequence 跟 R bigger than zero。
么叫所有的？
就所有的 sequence on R，就是
为
我知道对于所有的 R bigger than 0，我当然可以挑 sequence，
OK，
但是我现在是 show if and only if， 就是所以说我怎么知道就是对所有 sequence 就对 R bigger than 0，就是哪里怪怪的。如果就是像我这种方法的话，就是你 show left in right in left 就很简单。但如果直接if and only if， 我想不到。
哦，OK，喂，有一个方向比较难，你知道？
对，就是
你的问题是什么？所有 A 的点
就是
哦，你是说对于这些 R 没有，但是为什么对于所有的 R 都没有？是吗？
就是这个无所谓，这个就是一个复刻的方法。但我总觉得就是
对，确实，
但总觉得这个 proof
确实好像可能好像觉得应该是少一些东西。
对，就是它可以就
像我觉得
exist some R in A exist some R this 这个
对，你是说会掺杂？
对
OK，我觉得合理，也不是掺杂啦，就是说来你到了一个 R 过后，应该就要
在里面
啊，对，OK 好。
你可以
哦，这里面全都是 I 人。
不停的一个符号或者是从那个
看得到的看谁吧，还是谁在玩？
你不要什么哎，他那所有的 interior point 已经是完全对，应该是你还说了地方呀？原来说他有他用19的，这个放在你的榜位上。但是我突然一下子没反应没有，
没有啊？
我觉得他这一点很伤感。
什么？
你看
那点
那里面快
什么？
过到很有压力，
周末你这样想他，你周末不觉得他很开心？
因为他身边有的人不要做到极致啊那种。
很开心。
先问一下你这个图怎么？
还是那个关就是一没有人就是空无一人。
哎，所以有什么有什么例子？他是 interior point，但是他不是那边画出来，突然我发现行啊，对不对？M 就是
有一个波我在里面的，然后那个波它附近有没有？ Well， I mean 跟你讲，每件事情有好坏，有两个方式看它。
我是觉得啊，是讲那种要 space 的话，
我觉得给一个没有情绪的东西赋予希望就是没有意义的。
确实极端，因为他就是
要不就把他妈的，然后就是刚刚那种沟
哦，我还记得这个是零，这个是1，这个是2。
哦呀，
对。Again.
So
Yeah.
the argument should be
Ah.
is there a if the element of the R that intersect is AC is non-zero. It's not zero. If the element of R is not zero, then it's a isolated. I'm not isolated. It's in.
你这是新的 statement，新的 statement，新的 statement。你可以写一个
尝试去就是
找
explain 这个 idea，就是它因为它 R 大的时候它就可能会 insert 外面，但 R 小的时候可能就在里面。这样，如果它一直就是 inside both 的话，它就是那个 boundary。就如果它的 element of R that inside outside is zero，那就是 boundary。如果
你写给我
OK，
我来记不起来。
OK，
写给我，再写给我。Okay, just now, there's one, I think we are missing some cases here. Actually, there's a clean way to do this. So let me go back. Actually, we're kind of missing cases here, this A, B here. Because it could be the case that sometimes you live in A first and then sometimes you go B first and then you move into A. Because when your ball gets smaller, then you eventually live inside A. Okay, so to cater all these cases together, then we just put it as X in X, and then for every radius greater than 0, BRX must intersect A non-trivially. Okay, must intersect A non-trivially. Okay, so that it cannot live entirely outside. Okay, does it make sense or not? If there doesn't exist a ball that you can live outside, why? Because every ball must contain a member of it. Okay, and then from here you actually can use part 4 already. Okay, you can use part 4 here. Part 4 says what? Part 4 says that. Part 4 says that every point in A bar is either a limit point or an isolated point. So both these points will intersect A non-trivially. Yeah. Okay, so use the part 4 here, cleaner. Oh, and then the other thing is, I think there's something wrong here. Here is just strictly less than subset inclusion, strict inclusion. Yeah. Then because due to the A bar, due to the boundary of A, right? Because A bar contains boundary of A. They already strict, so you cannot fill that in. All right, so continue. So we're gonna introduce the definition of open now. Okay, in the metric space, here we define open in a metric space. So a set in the metric space, X is open. We will say we'll put if and only if here instead of if, because okay, I don't want to explain. So because not because if and only if A bar is in interior of A. Okay. I mean, there's a very interesting way to think about this, you know. Just now we see that an open ball, right, is open, but it also satisfies in A equals to A. But here we only require one direction. But the other direction is always true. In A is always in A. So actually, when we impose this direction, we already imply A equals to A. So if you want to be open, you have to be inside your interior. 你要接受你的内心，你才够开放。You need to accept your interior first. 所以你要开放，你要接受你的内心。OK， 要接受自己。Yes. All right. Anything to check here? Let's see. Okay, let's make some remark here. So like what I said just now, A is open if and only if A is equal to the interior of A. Second, a set A, they just use A. A is open if for every X in A, there exists a ball, okay, that contain X is in A. Okay, in particular, yesterday you saw this kind of definition before. Ball inside a set. Yesterday we have this notation, this terminology, right? Something that contains a ball, the center of X. So we say that A is a neighborhood of X. With a ball. Okay, so actually that neighborhood is open. Okay, it's open. So whenever you see the definition like this, if and only if, right? So meaning if we define open in different way, these definitions should be equivalent. This definition should be equivalent. Okay, so for example, there are very easy open set you should know. One is empty set, one is the whole space itself is open. Okay. Is it easy to check or not? What is in A? There exists a ball. What is in A? Okay, so let's try. Do we have phi inside in phi? Do we have x inside in x? In phi is what first? Why is it nothing? Huh? What? Huh? So someone suggests claim that in A is empty. Why? Subset of nothing. So where do you pick in A from? You should pick from matrix space, right? X. Okay. You take an X point from X and build a ball, and that ball live inside empty set. Why? Huh? Why? Empty set is an empty house. No one live there. Okay, none of the ball can live inside. Huh? What? No house. Empty house. Okay, no one live there. Okay, so no ball can live inside. Okay, it's empty. So obviously, empty set is a subset of empty set. You see, go back to set theory. Empty set is a subset of empty set. This we prove, right? Empty set is a subset of any set. Okay. How about in X is in A, in X? What is in X? Yes. So what is it? Can you identify what set is that? Okay, so I put down the logic here. Since you think first, I put out logic for the previous one. Since in empty equals to empty, we have empty set inside empty set. Second, since in X equals to X. So the second reason is also X is a subset of X. You see, both reasons go back to set theory. And then you need to know that a set is a subset of itself. Empty set is a subset of everything. Okay. Okay, next. Proposition. Will show that actually int A is open. Okay, actually int A is open and also XA. Okay, both of this set is open set. Yeah, let's see how do we show int A is open, and then we will left XA as an exercise. It's the same thing. All right. So what to do here? I want to use an open ball definition. Should I play cheat or not? Should I prove it to you? So never mind. Let's talk about the equivalence between these two first. Okay, so if I assume that A is in the subset of in A, right? Can I prove that A is, you can do this process here. Okay, if A is in A, this open ball condition is true. Okay, let's call this an open ball condition. Open ball condition. Can you show that they are equivalent? Okay, so let's put a lemma here. So A is a subset of in A implies if and only if the open ball condition. Okay. So should we prove this? Okay, let's do it. Excuse me. Okay. Two direction. One direction. So if you want to prove the open ball condition here, just take any arbitrary x in A. Okay. Can you find the open ball condition or not? Why? Since x is in A, which is in turn in A. So in A definition says what? There exists a ball around x, which is in A. Okay. The other direction, you want to show that x is in A, right? So similarly, you take okay, never mind. Since x is in A, now what do you do? By the open ball condition, who says something? There's this here x is in A, which is what? Which implies that x is in A. It's really the same thing. I just try to write down the in A definition. It's the same thing, right? It's the in A definition actually. Okay, in A actually is the open ball condition. Okay. Although you see different words in A, open ball, but we define in A as an open ball condition. Okay. All right. So let's do this. So we want to show that in A is open now. So meaning we need to take a point in A. Okay. And then try to show that. There exists a ball around X which is in A. Okay. So what's this doing? What's this guy doing here? Okay, let's start. Let's start from the assumption. There's really few assumption. That's our assumption. Okay, just start with it. Since is X is in A, there is some ball such that ball with radius Rx is in A. Okay, are we done or not? Okay, the subset 1 Are we done or not? No. Okay, we want it to be in A. This one just in A. Okay. Okay. We want to show that it's in A. Okay. So now we have a claim here. Let's make a claim. So here's a claim. Actually, BRXX is in A. 俄罗斯套娃来了。BRXX is in A. Not just A, it's in A. Why? Proof? I claim I must prove to you. Okay, so prove it. Proof of the claim. Okay, so to show this is a set inclusion. What do? Take Y in BRXX. You want to show that? Want to show Y is in int A. Okay, but Y is in A means what? Just now I showed to you the open ball condition, right? That is, there exists some, let's call it Ry, such that Bry Y is in In where? Huh? In A? Huh? BRX. You mean BRYX? BRXX. You have to show that Y is in A. In A definition is what? In A. Right? There's a ball around around Y is in A. In A, yeah? Okay. Okay. Everyone okay? Definition. Don't confuse, Follow definition, Y is in A. Okay. Very sure that this is in A. So how here is the technical part. How to find this RY, given what you have known. So let's draw some picture here. So let's say this is A. Okay, you got some X inside your in A. Okay, let's draw it inner, never mind. And then you know that already there's a radius of Rx inside here, such that the whole ball is inside A. But now, what do you want to show? For all other Y's, right? So for all other Y here, can you find another ball to live inside A? Rx minus distance between Y and X. So meaning what? You don't want to take a too big open ball here. You don't want to take a too big one. Okay, such that we could use the open ball condition on X to show that this ball lives inside A. Obviously, from this picture, you can pick something larger, but it is not necessary. It is not necessary. And the way of picking this is not very consistent also. Okay. But you can always pick a smaller one. Okay, you can always pick a smaller one here. Okay, so you can always pick a smaller one. Okay. So what's this radius here? Yeah, so what's this radius here? Is Rx minus the distance between Y. Okay, then you need to show it. Okay, so you need to show it. So we want to choose Ry actually equals to Rx minus dxy. So let's show it. So from the picture suggests that this could be true. So let's show it. So let's consider P of Rx minus dxy y now. Now you want to show that this ball is inside A, meaning what? You need to take any point from this ball again. Okay, you need to take every point from this ball again. Show that what? If it lives within Rx, okay, from X, then you are good. Then this whole ball will sit inside the ball of Rx. So if you compute Z minus X, okay, by triangle inequality, you can relate back to Z minus Y plus Y minus X. Okay, but okay, let's use D. Let's use D. No need to use this. Use D. But dzy is what? What is dzy? Where do I find the dzy from? Z is within the ball of radius Rx minus dxy from 1. Okay, so this is less than or equals to Rx minus dxy plus dxy. Okay, so this whole. Okay, so meaning what? This Z is Rx away from X. So meaning what? So this implies that the ball of Rx minus dxy, all the point here is just Rx far from X. But we know that the ball of Rxx is living in A. Okay, so we're done. So this implies that y is in. Since we know that y is in the interior of A, this also implies that Brx is in the interior of A. Okay? Okay or not? So what have we used here? We just use a bunch of definition of interior and then just triangle inequality. I can ask a further question there. If int A open or not? Huh? Interior of where is open? This was last year exam question. Interior of where is open? So you need to open. Okay, another way is you can reuse this one because in A is the interior of in A one. So you can use this. Or you can try and imitate this proof again. Take point from in A. Yeah. One way you can use this, apply this proposition, or do the original proof again. Yeah. To see you are familiar with the triangle inequality and familiar with the definition of in A, right? Interior of some set. Okay. Okay. Let's see. I'm not sure why I put that exercise. I think I will get rid of the exercise. Okay, never mind. Okay, next. Okay, motivation here. Let's see some motivation here. So, if you know about the open set in real numbers, let's take this union from 1 to n. What did you get here? What did you get here? What do you get here? Hey, what am I writing here? What's this? I think this appeared in your one of the class assignment, right? I saw it before. What's this? Huh? No, this one over n, usually over n. Yes, -1 to 1. Okay. So if you write it out, right, what do you get? -1 to 1 union, -half to half, and then keep going on, or to union -1 over n to 1 over n. So what do you see here? You go from a larger interval to smaller interval, but the larger one already contains the signal. Okay, so you just left with the larger one. Well, if you take intersection, infinity intersection of 1 over n to 1 over n, what do you get? You get just a point. Okay, so you can see that finite union, you still get open interval. Finite union of open interval still open, but infinite intersection of an open interval become just a point. Kind of close, right? So can we write this? We didn't define yet, right? So better we don't write this. Okay, never mind. Okay, just a point. Okay, just a point. For example, another example. If you take a finite union of closed interval, for example, this guy, what do you get? What do you get? 1, 0? 1, 0. Like this. Is it? Am I doing something stupid here? I think it's stupid. Quite stupid. It's stupid, this one. Let me see. Half go to half, and then 1/3 go to 2/3. Okay, let's write down what do you get. So 1, 0. Let's see. Wait, before that. So, okay. So let's see what we get here. So if I put 1s in, I get 1, 1 minus 1, so 0, good. Second, 1/2 and 1/2. Okay. Union 1, 3 and 2, 3. 1, 3 and 2, 3. Only here starting to make sense. And then continue. 1, 4 and then 3, 4. Okay. So how do we define this intervals here? So let's define it. So if I'm closing it, it is all the x such that x is less than equal or greater equal to a. Greater equal to a, less than equal to b. And if it's open, it is all the x such that. So where do I pick this x from? So better we don't make the Russell paradox problem here. So let's specify where we pick them. And if it is open, then it is strict. Okay. So in this case here, you can see that this guy should be empty. There's no point can be greater than 1 and then, yeah, less than 0. And then this guy here, the next one is just half. Okay. And then if you keep union these, what do you get? Open what? Open set from 0 to 1. No, I mean my thing will stop with n, right? Which one is big? Which one is small? I think this one quite. I don't know what am I doing here. What do I why am I writing here? Okay, let me tell you what answer I get here. See how to amend this. Okay, actually I want to put something in front this closed set here, such that I can get 1 over n to 1 minus 1 over n. So you can see that, what can you see here? You can see that in the previous case, right, the interval actually getting smaller, smaller, right? So the last one should be the smallest one. How do I get the smallest one? 不懂，你有大的东西哦，越来越小，越来越小。你要怎样拿那个最小的东西 ？Union 还是 intersection？intersection， 因为那个小东西就活在每个大东西。Okay, so you should take the. Actually, I should consider the intersection. Okay, so what I want to show you is intersection of finite intersection of closed intervals to close. Okay. But if you take the union to infinity of a closed interval, what can you see? What can you see here? It is actually a open interval from 0 to 1. Okay. Okay. Is it true? 还是错啊？又是错。我要怎么拿到它到底？是越来越大？哦，越来越大。怎么刚才想到越来越小哎 ？Let's draw it. Let's draw it. Let's draw it. 来，我们画一下，画一下就没有好讨论了。来，画一下，画一下。一个是1/2 ，right？ 从1/3到2/2看，左右边。OK。呀，怎么刚才讲越来越小，怎么没有人讲呢？没有讲话啊？是不是？没有人想知道我在干嘛？原来在关山。Okay. So where is 1/3, 2/3? Okay, where is 1/4, 3/4 here? 1/4 是在这边。Okay, 3/4 is on the other side. Okay, so let me draw it. So 一个是 half, the other one is 1/3 to 2/3. And then the other one is 1, 4, 2, 3. Okay, then I think we're good. Okay, I think we're good. Okay, so if you take infinite union, you can see that it grows closer to 0 on one side and then closer to 1 on the other side. Okay, but you never reach 0 or 1. Okay, you never reach. Okay, all right. So what can you observe here actually? So the theorem is if A1, A2 up to AK are finitely many open set here, then if you take finite intersection, it is still open. Finite intersection is still open, okay? But if you take arbitrary union, I don't care whether it's finite or infinite. Okay? Don't care whether it is infinite or finite. If you take just the union of it, it is still open. Okay. What time is it? Yeah, we still got time. Let's see. 1, 2, 3. Yeah, let's quickly do this. Let's do this. Yeah, let's do this. There's some technical point you can see here. Okay. Let I be a finite index set. We will first show that. The finite intersection is empty. Sorry, is open. To show that it's open, what do you need to do? Just now say it is equivalent to the open ball condition. Okay, you want to find a ball around X that lives inside all the AI. Okay, live inside all the AI. So let's take X in this intersection here. Then how to find this ball? You need to use assumption here. These AI are open. Okay. Since it is in the intersection, obviously it is in all the AI. Okay. But all the AI are open, meaning what? There's an open ball around X in each AI. Each AI. Okay. But the problem is all these balls could have different radius. Okay. All these balls could have different radius. How? Can you cook out another ball that live in all the AI based on these RI? How? You take the minimum, okay? So then we choose R to be the minimum model. Okay, so we need to show. Okay, so we need to show it. So we need to show that BRX actually live inside BRIX. Actually live inside AI. Is it true? For all one? True or not? True, right? Because here it just says that if your, let's say, okay, let me put a bracket here. Here it just says that if your y from distance from x is less than r, obviously this r should be less than or equal to I. Okay, you live inside the ball of radius I. Okay or not? Okay, so since it is true for all I, by the set theory definition of intersection, BR will live inside the intersection. Because if you want to stay inside the intersection, it has to be true for all I. I will show it for arbitrary. Okay? Can or not? How about second part? I think second part is easier to show that the union, okay, is open. What do you need to do? What do you need to do here? Take an arbitrary X again from where? Should be taking from the union, right? Something wrong in my previous proof. Okay. So if you are in the union means what? What's the set theory? There exists some L such that X is in A, L. Okay. Lambda, thank you. Okay. A lambda here. But again, there's not much thing you can do here. You only know that A lambda is open. So try, again, since A lambda is open, it means what? There exists an radius Rx greater than 0 such that Brx is in A, L. So meaning what? You are in one of the A lambda. Obviously, it is also in the union of all the A. You already stay in one of the A. Okay, so hence, a union of A lambda is open. Okay, so done here. Okay. So what can you see here? Okay, I think time's almost up. So what can you see here? So here's the theorem. In a metric space, XD, what can we see here? Actually, the empty set and X are open. Okay, just now I show you. Because just empty set is a subset of empty set, X is a subset of X. B, finite intersection of open set are open. Lastly, we prove that arbitrary union of open set are open. Okay, only B needs some technicality, choosing the minimum R. But C, any R will work. Okay. So from here, we'll generalize it to topological spaces. Okay, so what's the topological spaces here? So topological spaces is a space with a set of open set that satisfies the axiom ABC. Okay, so meaning what? If I have a set, I have a collection of open set. Okay, I need to declare who is open. Okay. When I declare who is open, right, I have to make sure that ABC holds. Meaning what? From part A, you will see that the empty set and the whole set should be one of the open set. And then once you pick all your open set, right, you need to make sure that the finite intersection of open set is still in the one of the choices of open set. Okay, and then you should consider all the arbitrary union of the open set you declare is still open. It's also one of the open set. Okay, then this is a topological space. Then there's no more distance anymore. So you see from distance, we extract out the property of open set. And then we try to define a set without distance anymore. We just call some set as the open set that satisfies this tree property. It turns out that it's enough for us to get interesting result and generalized result in analysis. So what kind of result can be generalized? For example, compactness. Okay, you want to use what's compactness again? Every sequence has a subsequence that converges. Okay. So in here, later you won't see subsequence anymore. Then you will see something else. Connectedness, half connectedness, okay, also can generalize to topological space. Okay. Okay. Any question? No? Okay. In next class, we will prove more property on this closure stuff, and then we will move to topology. Okay, any question before we finish? No? Okay, then we'll see you next week.